These notes are over kinetic energy, and this should be kind of a review from your physical science class. You should have talked about kinetic energy in your physical science class, and you probably even saw this equation in your physical science class. So kinetic energy is just the energy of motion, and it's dependent on two things, the mass and the speed of the object. Okay, so kinetic energy is measured in joules, and here we have that the energy, specifically the kinetic energy, is 1/2 the mass times volume squared, or velocity squared. Okay, so like I said before, they're both dependent on mass and speed. And if we look at the equation, okay, you'll see that velocity is squared, whereas mass is just multiplied. So kinetic energy is most dependent on your speed. Okay, so if your speed increases, it's going to be squared, whereas if your mass increases, it's just being multiplied. Okay. So like I said, kinetic energy is measured in joules. Okay, and I'm going to just kind of show you this page. I'm not going to talk through all of this, but this is the derivation of the kinetic energy equation, breaking down work. Remember that work is a change in energy. And so since we're looking at energy, we can substitute in the formula of work. It also uses one of the kinematic equations in order to kind of break it down. But the necessary information is that kinetic energy equals 1/2 mass times velocity squared. So this equation implies that two objects with the same mass moving with the same velocity are going to have the same amount of kinetic energy. Okay, so if they're two different shapes but they have the same mass and they're going at the same speed, they're going to have the same kinetic energy. If two objects with the same mass are moving with different velocities, the object that's moving faster is going to have more kinetic energy. Okay, so if we had a velocity of 2 compared to a velocity of 4, okay, the one with 4 is going to, in turn, increase the kinetic energy. Okay. If two objects are moving with the same velocity but have different masses, then the more massive object has more kinetic energy. And like before, we talked about the faster you are can increase the kinetic energy more so than how massive you are. Okay, so if we look at the compared kinetic energies of these two different objects, first, we have your mass. We could say that you are 65 kilograms and you're stationary at your desk compared to a snail of a mass of 15 grams moving at 0.00001 meter per second. Okay, the snail is going to have more kinetic energy because you are not moving. Okay, your velocity is 0, and so if we were to plug that into the formula, your kinetic energy would be 0. The snail, although it would be very minute, would have kinetic energy. Okay, if we're looking at these two, we have a fly with a very small mass moving at 1.5 meters per second, and then we have an RV with a very large mass moving with a velocity of 20 meters per second. So the RV has a greater mass and a greater velocity, so it's going to have a greater kinetic energy. Okay, for these two, we could actually plug in the numbers into our equation, so we could do 1/2 times 62 times 12 squared, and then this one as well. And we'll find that this lacrosse player, even though they have less mass, because they are moving faster, they're moving fast enough to increase or to have a greater kinetic energy. Okay, same thing with these two things. Even though electrons move very, very fast, they are so small that a larger oil tank that is moving slower would have more kinetic energy. Okay, for an accelerating object, it is the change in kinetic energy. So we would have the ending kinetic energy minus the starting kinetic energy. Okay, and so we can expand it out to this. One thing that you'll see that I'll kind of break down in our practice problems is that we can kind of simplify this equation into 1/2 m and 1/2 m times the difference between V2 squared minus V1 squared. Okay, so I'm not stating that it's this. We can't pull the squared out of this. We need to square both V2 and V1 and then find the difference of those two. okay? So just be careful on that. And like I said, whenever I go through the examples, I'll kind of write out that equation with. So for example number 1, it says determine the kinetic energy gained by an ATV, which has a mass of 285 kilograms, as it accelerates from 2.6 meters per second to 1.8 meters per second. Okay, so here we are accelerating, so we will be using that other equation that I was just talking about. Okay, so for part A, we're going to be using the equation change in kinetic energy equals 1/2 mass times the difference of V2 squared minus V1 squared. Okay, I can't pull the squared outside of the difference of the two. Okay, so then I just plug in my information. So I'm going to have 1/2. My mass was 285. Okay, and then my V2, my final velocity would be this one. This is my V1. So 8.1 squared minus my 2.6 squared. Okay, and I will get that my change in energy is 8,386.125 joules. Okay, for part B, it says what type of energy could have been transferred for the ATV to gain kinetic energy. Okay, so remember, kinetic energy is motion, and so this is kind of going back to whenever we were talking about transforming energy. So if you wanted to speed up a car, so an ATV is like a vehicle, if we wanted to speed up or accelerate in a car, you would hit the gas, okay? So the more gasoline that is burnt, the more kinetic energy it's going to be converted to, okay? And so that fuel being burned is known as chemical energy. Okay, so it's going from chemical to kinetic. And it's being converted to other things as well. We could also say that it's going from chemical to thermal because it's also producing heat. That's why your motor is warm when you're driving because it does release heat as well. Okay, and then for part C, if this acceleration took 14.3 seconds, what's the power of this energy transformation? So for C, remember that power is change in energy, or it can be work, which remember work is change in energy, over change in time. Okay, so we just calculated the change of energy, which was 8,386.125 divided by our change in time, 14.3 seconds. And we will get that our power was 586.44 watts. For example number 2, a shopper pushes the shopping cart, which gives us the mass, with an applied force of 26 newtons through 30.8 meters. If friction is negligible, for part A, how much work is done by the shopper to the shopping cart? So remember that work, it is change in energy, but we can also break it down into the applied force times the displacement times the cosine of theta, where theta is the angle from the direction of displacement. Okay, so for this one, it gave us that the applied force was 26 newtons. The distance or displacement was 30.8. Okay, and you are pushing the cart in the direction of the displacement, so it is going to be of 0 degrees. And we get that work is equal to 800.8 joules. For part B, if the shopping cart initially had a speed of 0.8 meters per second, what is the final speed? So it gave us V1, but it wants to know what is V2. Okay, so remember again that work is the same as a change in our kinetic energy. Okay, and we can calculate out our kinetic energy with velocities as 1/2 mass times V2 squared minus V1 squared, okay, would be equal to our work. So we just calculated work. So we're going to have 800.8 equals our 1/2 times our mass, which is 38.4, okay, times the difference of V2, which we don't have, that's what we're trying to calculate, squared, minus our V1, which is 0.8 squared, okay? And so now we just have to solve for our V2. So we would multiply these two together and then divide both sides by that value. And then we would square the 0.8 and add it to the other side and then take the square root of the whole thing to get that our V2 is equal to 6.51 meters per second. For your practice problems, the biggest thing that you need to consider is that a lot of them are going to give you the wrong units, where they might give you kilometers per hour. Yeah, these two are in kilometers per hour, so make sure you convert them to meters per second before you start. Okay, for question number 1, it's going to be pretty simple. We're just going to be plugging into the basic kinetic energy equation, the 1/2 mv squared. For the second one, they're giving you the energy, the amount of kinetic energy, and then you just have to find the velocity at which it's has that much kinetic energy. So again, using that kinetic energy equals 1/2 mv squared, then you'd have to solve for v. For part 3, you are having an acceleration, so remember you do need to use that the change in kinetic energy is equal to 1/2 m and then times the difference of mv squared minus v1 squared. Question number 4 I discussed in our notes prior, so hopefully you understood that part. And then for question 5, you'll see I have 2 equations written down here for you to just help you. So first you'll want to, so this is very similar to the question number 2 that we did. So first you'll want to find the work that was applied to the curling rock, and then plug that into this equation in order to find the speed of the final speed of the rock after it's traveled a certain distance.